Hey guys, so as you can see on the title, today I'm talking about of an article that I wrote to MIT, and it's about how to couple spinors to gravity. Actually, it's about loop quantum gravity, LQG for short, right? And why it's very difficult to introduce spinors into general relativity, and that is a very important thing because we need to introduce spinors to gravity to general relativity if we want a theory of everything or a theory of quantum gravity, right? So anyway, the big problem actually is that there are no finite dimensional spinorial representation of the gravitational gauge group, that is the GL4. There's a lot of formalism, math behind of this physics, but I will just focus on the physics behind, right? I won't talk about from all those mathematics behind of that. I will skip some steps and just talking about the article. So how there are no finite dimensional spinorial representation of the gravitational gauge group, that is the GL4. As I say, this is a big problem because it's not therefore obvious how to introduce spinors into general relativity. And we need to introduce spinors to general relativity if you want to construct a theory of quantum gravity. So the solution is as follows. If we consider only one single point, let's say here, on a curved manifold that can be a Riemann manifold, I don't know, but just a manifold. Alright, a manifold. So if I take a vector here, I don't know, x alpha, at exactly just this point, the manifold is exactly approximated by its tangent space at that point. So if I take an decimal element here, so as I say, at exactly just this point, the manifold is exactly approximated by this tangent space at that point, let's say P, right? So what we need is, if one is using a Lorentz curved metric, the tangent space at their point will be the Minkowski space. That's obvious, I hope you know. So one can then define a field at this point on the curved manifold that is a scalar under GL4, but is a spinor representation in wall 3.1. So here is a scalar over this transformation, this group, but is a spinor under. So here we have a spinorial representation. Spinorial representation. So, given all those considerations, the first thing we can do is write like a Dirac-Lagrangian density, L Dirac, which is psi bar I gamma mu capital D mu. Sometimes you will see this like this symbol here, and always that we have some gamma mu D mu. Sometimes we call that D slash, but I won't do this because this gamma matrices here will be very important very soon. So it's just a notation, all right? Let me erase it here, and I'm gonna call this covariant derivative from D capital D mu minus M psi. Uh, Obviously, just a warning, I'm just using the natural unit, so C equals to 8 bar equals to 1. In the case of the general relativity, we get G equals to 1 as well, right? So here we don't have a C 8 bar, just I gamma mu d mu. And then when we take this covariant derivative capital D mu, acting on psi, what we have is just the ordinary derivative d mu minus I over 4. And then here we have omega a b mu sigma ab acting on psi. What is that? Those guys here are the generator of the group, right? And this omega ab mu is what we call a spin connection. Spin connection, which is an idea from loop quantum gravity, I hope you know. So given these AB indices here are the isospin, so AB isospin index. Isospin index. So, however, this is not enough. What we need to do, and that is very complicated, but there are some exceptions, but we can construct. Alright, to take care of this isospin indices, let me just write some relations. That is eta AB E A mu E B nu, that is equal to G mu nu, right? And it doesn't work if you are in I don't know, singularities, if you're talking about of bodies like black holes or something like that. There are some exceptions from this, alright? But we are not in singularity, so I'm gonna just give you those relations. This is G mu nu, A nu, E A nu, right? And I can write in E A mu equals to eta A B E B mu, right? So this determines the tetrad, what we call the tetrad. As I say, there is some exceptions. If we are in a singularity point, we cannot do this, but we are not. So there's no problem. And this determines unequally the tetrad in terms of the curved metric, and obviously vice versa. So now we can take account of the gamma matrices. This guy here, the gamma matrices by the Clifford algebra. The Clifford algebra, you know, has a particular relation, maybe the most important relation, of the anti-commutation of those matrices. I'm going to erase here. So what we have is we know that the anti-commutation, the relation of anti-commutation of gamma mu, gamma nu is 2 G mu nu, or if you are in the Minkowski space, it's just 2 eta mu nu. All right. The tetrad is relevant here because the solution to this anti-commutation relation can simply be written in terms of the ordinary gamma matrices using the tetrad. So, I mean, A. So E mu A gamma A is equal to gamma mu, and this new gamma matrices is called the curved gamma matrices, right? This finally fulfills the second requirement, and then we can carry on from the third and last one step, which is write a solution to the spin connection, this term here, A, B, mu, because it's one of the most important objects in the loop quantum gravity. So to do this, we are using the metroanalytic property. The metroanalytic property is as follows. If I have capital D mu A, capital D mu E A nu, that's equal to the ordinary derivative E A nu minus the capital gamma lambda mu nu E A lambda plus omega mu A E B nu, and that's equal to 0. And as I say, I will skip all those mathematical formalism and just solving the equation from solving the equation for this guy here, the spin connection. So solving for a spin connection, it gives omega mu A B, that is equal to, that's a big term, 1/2 of E A nu D mu A nu B minus D nu E B mu plus 1/4. Here we have E A rho E B sigma, and then D rho A C sigma minus D sigma A C rho, and here E C mu, right? I don't have a lot of space here. So finally we can write, then when we solve for the spin connection, we can write now the action, and the action is given by the Lagrangian density. And what we're gonna do now is just combine the Dirac Lagrangian density and the Einstein-Hilbert action to write this new action, right? So you know how we do that to get the equation of motions, and we get two equations of motions that I hope you know, the Dirac equation and then the Einstein field equation, right? So the third requirement is fulfilled. Therefore, the generally covariant Dirac action coupled to general relativity is, as we know, S is equal an integral of d4x times the Lagrangian density, and the Lagrangian density here will be just the square root of minus g, which multiplies our psi bar E gamma mu d mu minus m psi plus 1 over 2k times the Riemann curvature tensor R mu nu rho sigma g mu rho g nu sigma minus 2 lambda. Alright, I'm sorry, here, and then the equations of motion are the Dirac equation, psi bar I, I will write d slash minus m psi, that's equal to 0, and R mu nu minus 1/2 of R g mu nu plus lambda g mu nu is equal to 8 pi t mu nu. Remember, right here, C equals to G equals to 1 to general relativity. To quantum mechanics, C equals to 8 bar equals to 1. We can always find this natural unit system. So here we don't have G and even C, this factor. And the source of energy and momentum here is given by T mu nu is equal to I over 4 psi bar, which multiplies gamma mu d nu plus gamma nu d mu minus gamma mu d nu minus gamma nu d mu. And here we have a psi, right? Multiplicating those terms. So it's just that, as I say, there is a very complicated mathematical formalism behind of this, but I will skip all of those things. So in another video, in a future video, I will show you how to couple the quantum electrodynamics and quantum chromodynamics to the gravity, to the general relativity. I know that the gravitational field is non-renormalizable, but there is a way to do that. It's not very easy, but nothing what it seems, right? So that's it. That's the way we couple spinors to gravity. We just take the Clifford algebra. We just need an observer that take a transformation that is a scalar under GL4, but simultaneously is a spinor representation, spinorial representation under O31 gauge group, right? So that's it. I hope you understand and you like, and that's it.